Okay, so let's look at this one. So what about this shape? Think about, guys, shut up back there. Think about this. Do you see what's going on here? Do you guys see those little, oh, I'm frozen still. You don't see me drawing on that. You really can't see it anyway. Can you see that where I drew in green? Yeah, so I have to go right through that. Who said that? Parker Yates. It does have 10 lines of symmetry. So Parker's counting this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's what Parker's doing. Good job, Parker. There really isn't more. There's really only 10 lines. We go through this. We go through this. We go through this. We go through this. I don't think so. Maybe there is. I don't know. I'm not going to count it. I'm not going to waste my time. Let's talk about rotational symmetry because this is important. Can you guys see the red ink? A figure has rotational symmetry. And Jack, as soon as I get done, I have notes printed. I'll give filled out notes. You'll get a copy of them, okay? Has rotational symmetry if it can be mapped onto itself. I really can't spell. By a rotation. And we tell the degree of rotation. So it's going to be between 0 and 360 degrees. Okay? So it's going to be between 0 and 360 degrees. When we talk about the word order, order is the number of times a figure maps onto itself as it rotates. Okay? And when we talk about magnitude, we're talking about the angle of rotation. So it's the smallest angle through which a figure can be rotated so that it maps onto itself. Yeah. It's the smallest angle. So there's a way to figure that out. So that's what we're going to try and do today. We're going to try and figure out the order and the magnitude of symmetry, of rotational symmetry. So let's look at this first shape. If I were to rotate this star over this much, just move it from here to here, would all the pieces line up exactly to where they were?
Yes.
Yep. So that's 1 time, 2 times, 3, 4, and 5 times. Okay. So this has an order, right? This has an order. It's the smallest number. Has an order of 5. Okay. Let's think about the magnitude. How many degrees are in a circle? Yeah. So if I want to find the magnitude, I'm going to take the total degrees in a circle and I'm going to divide it by the order, the number of times that it maps onto itself in 360 degrees. So 360 divided by 5 is what? It's 72. That means every time I rotate this, I'm rotating it 72 degrees. Each one of these moves represents 72 degrees. From point to point, vertice to vertice. Yes. Okay. Does that make sense? What do you think? So what if I wanted to go from here? This is the far right. So I would have to take this and take it all the way to here. So I'm really thinking about rotating it like this. This is the direction that I'm going. So like if we think of this point as being on the right and this is on the left, well, this is on the left and this is on the right. So it's going to have to go to here. So I can do it 1 time, 2 times, say it again, 3. So this has, say what? Yeah, so it has an order of 3, and it has a magnitude. I'm going to write it out. I know you guys are doing the math in your head. So 360 divided by 3 is 120 degrees. Good job. So that means each one of these movements, each one of these is getting moved 120. Every time I rotate it, I'm moving it 120 degrees to map it on itself again. 120 degrees to map it on itself again. Okay? So I'm going to let you think about C. Don't do any shout outs. Give everyone a chance to think about it. Count how many loopies you can make to map it onto itself. Everybody think they've got something figured out? Or you still need a little bit more time? A little bit more time, sure. All right, I'm going to show you. So here's my little center. So if I'm rotating it, think of this center on these as like the origin, right? Because we rotate about the origin. So I could rotate it 1, 2, 3, 4. I could rotate it 8 times. So this has an order of 8. So how much am I rotating it each time to make it map onto itself? 360 divided by 8 is 45 degrees. So the magnitude is 45. Do you guys understand that? Does that make sense? Good job. You guys know that we don't typically teach this to Math 2. It's only supposed to be taught to Math 2 honors. You guys are smart. You can do this. I do have great confidence in you guys. So sometimes we are going to think about three-dimensional objects like a box. Think of that box as a box of Kleenex or a shoebox, okay? So a three-dimensional figure has what's called plane symmetry. And it has plane symmetry if the figure can be, again, that fabulous word, mapped. Oh my God. I have a new battery in here. Can you tell? Yep. If that figure can be mapped onto itself by a reflection. So rotational symmetry is done by rotating, and three-dimensional, we do it by reflecting, okay? So I want you to think about if I were to take this whole piece and I were to reflect it across this, and this would get reflected across the plane. It's going to have one line of plane symmetry, but it also has a line of plane symmetry this way. Do you see that? Much like the rectangle that we started with. Okay? Just 2. Does it only have 2? No. What if I go through it? I'm going to mess up my drawing, but what if I go through it? Yes, I see someone doing that. What if I cut it like this way? Yeah. So it's not a square. You're thinking if I go this way? Yeah. So we're talking about reflection. So when I reflect this, it's going to end up here, not here. When I reflect this, it's going to end up over there. Does that make sense? But that's a good question. What? What if you reflect it 180 degrees? We don't reflect 180, we rotate. Well, it's reflection symmetry. Yeah, you're making it harder than it needs to be. Don't. Just think about it, how you can cut. Just think about a block of cheese, how you can cut it to make two pieces that smash back together to what it was originally. Just think of it like that, okay? That's how I want you to think about it. The two pieces that you cut apart are congruent to each other, okay? A three-dimensional figure has axis symmetry if the figure can be mapped. Oh my God. I'm going to give myself a concussion or poke my eye out. If it can be mapped onto itself by a rotation. So this is a cone over here, right? So if I were to take this cone and just rotate it, it has axis symmetry. Well, I didn't put any questions of this on your test, just so you know. Yep, because I just think it's not important. This is not important. This, though, just is the same idea. We're taking a three-dimensional shape. Is there a way that I can fold this in half, whether I rotate it, reflect it, or anything, and make it look like it has plane symmetry or axis of symmetry? No way. What about this one? Well, I can cut it right here, like, and I have two what? Say again? Yeah, I can cut it here. I can cut it here. Like, I can just keep spinning this little flappy thing all around like this, right? I can just keep cutting it and cutting it and cutting it. So this has both. This has both plane and rotational symmetry. Okay. And yeah, we can talk about these shapes, I guess. So let's look at some shapes. Tell me what an equilateral triangle is. Yeah, three sides are congruent. What else do you know about equilateral triangles? What does that mean when I do that to the angles? Do you guys know? Huh? No, if they're not 90, that would be a box. Say, what'd you say? 60. Yeah, they're 60. It just means when I put that little shape in here, like when I mark it like that, that also means that the angles are congruent. Do you guys see that shape I'm drawing? I'm drawing an equal sign and then I'm putting a little squiggly over it like that. That means congruent, yeah. Okay, that symbol means congruent. So an equilateral triangle has three sides that are congruent, but also all three angles are congruent. So does this have line symmetry? Well, I can cut it right here, or I can cut it right here, or I can cut it right there, right? So how many lines of symmetry does it have? Three. Okay. What about this rectangle? This is like our first example. Well, I can fold it hot dog style or hamburger style. So yes, it has line symmetry and it has two lines. What shape is this? Square. So let's see, I can do this or this, but I can also do this and four. So yes, four. This next one, and I'm going to tell you something. So a square is from the family of quadrilaterals, but it's also called a regular polygon. That might be something, and so is an equilateral triangle. Regular polygons mean that all of the angles are the same and all of the sides are the same. So when I look at this hexagon down here, it's a regular hexagon, meaning that all of the sides are the same and all of the angles are the same. Okay, so a square and an equilateral triangle live in that kind of regular polygon world. So hopefully we'll learn something about them. So tell me about a scaling triangle. No lines of symmetry. Okay, so let's look at our hexagon. So I'm going to erase all the marks that I just put on here. 6. I can cut it here and here and here, but I can also go right in the middle of those. So it's funny that a hexagon has 6 sides and 6 lines of symmetry. So it's a regular polygon. A equilateral triangle has 3 sides and 3 lines of symmetry. And a square has how many sides and how many lines of symmetry? 4. So, So let's look at a pentagon. How many lines of symmetry do you believe this has?
0.
What? Is that not a fold? Don't look at that.
I thought I had a few more.
Shh. Well, it's regular, right? So what can you tell me about it? My picture is hideous, but how many is that? Go from every vertice to the opposite side. Every vertice, so every point here to the opposite side here. That's 1 line. Here to the opposite side. Yeah. So I wasn't planning on drawing the lines because I was trying to get you guys to see what I just said. So an equilateral triangle has 3 sides and how many lines of symmetry? 3. A square has 4 sides and how many lines of symmetry? 4. A hexagon has 6 sides and how many lines of symmetry? So a pentagon has 5 sides and 5 lines of symmetry. It's because they're regular polygons, meaning all of their sides and angles are congruent. What does it have cut out of it? Okay, so we can still fold those in half though, right? Yeah. Do we understand that? No? What about F? Let's talk about it. Well, it's an isosceles trapezoid, so let's talk about what that means. Isosceles trapezoids mean that the legs, that's what these are called. This is called the base, and this is the base. These markings, I've done this before in this class before, I think, maybe. What do these marks mean when I put 2 red triangles on a line? Yeah, yes, say that. They're parallel, Tyler. These 2 lines are parallel to each other, and that's the definition of a trapezoid. A trapezoid has 1 pair of parallel bases, and then the other sides are called legs. If it's isosceles, these 2 legs are congruent to each other. So since those 2 legs are congruent, when I cut this in half right down the middle, it will split, fold onto itself. So this has line symmetry, but it only has 1 line because it's not a regular polygon. Okay, so I'm going to write a little note down here to make sure you understand what regular polygons are. So regular polygon, it means that all of the sides are congruent. Are you okay with me using that symbol? And it means that all of the angles are congruent. Are we good? Okay. We the number 2 using rotational symmetry. Yeah, it can. You guys should have, but then you have other pages of homework too. Here, wait, let's go through it. So yeah, we'll do that because I want to get you guys. Some of you guys need to finish your quiz. So we're gonna make this because I already scanned this. We're gonna make this homework. Oh, it's coming up. You can skip the whole Anna Bob Otto thing. You're just going to do number 2. Don't worry about this Anna Bob Otto. I'll do that with you tomorrow. Okay, so you're just going to do number 2. And then if you go to your next page, if you go to your next page, it looks like this. Give me a second. Let's just pick the problems that we think are going to be good. I don't think that you need to do 1 through 3 at all. Cross it off. I want you to do 4, 5, and 6. Is that okay?
Yeah.
You'll do 4, 5, and 6. Skip 7, 8, 9, 10. I want you to do 11. So we're going to do 4, 5, 6, 11. 4, 5, 6, 11, and 13. 4, 5, 6, 11, and 13. Deal? Nope, don't do 14. You're not doing them. Okay, so Jack, will you do me a favor? If you go up front where that little white, there's a little white plastic thing and it says period 4, your filled out notes are right on top of it. So you guys are going to do number 2 from the notes, and it's called rotational symmetry. And then, whoops. And then you're going to do questions 4, 5, 6. Numbers 4, 5, 6, 11, and was it 11 and 13? Yeah? No? Okay, you guys are awesome. It's right there. Give me a second.